Hello there, Alex here again, continuing with our series of how to master secrets of asynchronous programming. This is part 2. In the previous video, we introduced the concept of different computing models and architectures, and also different ways of looking at how to automate various processes. We did mention, if you recall, that most of the current way of thinking, or the mainstream way of approaching automating services, is based on the idea of sequential execution, the so-called imperative programming, where we are assuming a sovereign position. As the rulers of the universe, we can observe the process, we can pause any process, we can process turn our focus on the main process we are working on. We can let it finish and then press the pause button again to unfreeze the other waiting processes and continue from the point where we are ready. This, of course, is a extremely naive position, and the necessity for mastering the so-called asynchronous programming comes from the fact that as we are modeling or the reality of various processes, we need to take into account the fact that reality works in parallel, that there's many things happening at once at the same time, and it's very unlikely that some independent process is going to stop and wait for another one to finish. So continuing from that point, we are now moving into examining a bit closer the nature of asynchronous programming, and whether we can, afford to deal with more complex implementations following the continuous execution. For example, this is a sequential blocking, step-by-step processing, which is, okay if we have a series of computations within a single instance of computer memory, RAM, or, it's in a single location. But if the two or more instances need to communicate with each other, then the complexity increases. So whenever we have two or more processes that are happening, or instances of some kind of implemented model communicating with each other, we call that, in technical jargon, we call it input-output, or I/O. So whenever we have the situation with the input-output, I/O, it is risky to abstract, meaning to reduce to insignificant concern, this I/O portion of the implementation. We cannot just safely ignore it and say, well, it doesn't matter, it doesn't change anything, because that is a slippery slope, as we'll see. Whenever our implementation depends on I/O, and I'll just list some of those to refresh your memory, anytime we are writing to disk, the auxiliary storage, anytime we are connecting to a database or listening for end-user gestures such as mouse clicks and tapping on the screen, etc., or listening on a network port, and there's many other cases, all these I/O scenarios are adding complexities to our processing logic. If we decide to ignore those added complexities, say, well, yeah, I know, but I'm not going to concern myself with that, then it is a perilous situation. We do it at our own peril, and we may live to regret it, because it is kind of a slippery slope, or thin ice, or even quicksand situation, the minefield where things can go all of a sudden awry without even us realizing that something's going wrong. So what are the complexities that we can talk about regarding these I/O boundaries? There are things that we label as latency. Another issue is consistency, as well as the shared mutable state. And we'll talk a little bit more about that as the presentation progresses. So whenever we have a naive implementation, we see that these complexities are abstracted away. So For example, if I'm examining a unrealistic implementation of some business process automation, I often notice that latency and consistency and shared mutable state is completely ignored, and I find that a bit concerning and risky. Because this is potentially, when we ignore these complexities, we are creating a breeding ground for bugs, which are, sometimes very difficult to squish. And this is definitely not a breeding ground for achieving ultimate sophistication, simplicity, etc. If we are pretending that an I/O operation is in the same league as reading a value from memory or performing an in-CPU computation, then we are running a risk, because these two operations are not in the same league, not at the same level of complexity. And there's no two ways about it. That's how things are. So the question is, why is that considered risky? Why can't we just say, you know what, I'm not going to pay attention to that because that is just so much more work. I'm just going to pretend as if everything is happening here locally in my computer memory. So when we are reading a value from the memory, if we are fortunate to have everything, all the entire processing happening locally, meaning we are performing an in-CPU computation, then we need not be concerned about these issues typically. We can say, yeah, but I'm not worried about latency or consistency of my data or shared mutable state. I think I'm safe. And that is a pretty truthful statement, because in-memory computation should be instant. There shouldn't be any latency to speak of, because CPU is very fast and accessing memory is very fast as well. And even if they happen to not be instant, it doesn't matter, because no other processes are waiting for the outcome. There's no sharing. So we are pretty safe in that environment. We are not, if we're doing in-memory computations, we are not sharing any mutable state with any other process. So we are very isolated and safely snuggled away in our little sandbox. So we're talking here about continuous execution, where single-threaded in-memory computations, the series, the sequential steps, are happening from start to finish continuously, and there is no risk of these steps ending up in an inconsistent state. If they do, then there's error in programming logic, or error of some sort that is creating a bug that can be identified and fixed. Now, if we turn our attention from these in single location computations to computations that are involving input-output processing, where there is I/O boundary, we can't avoid the fact that I/O processing implies latency, implies some gap in time. So the process starts in one location and then has to communicate via the I/O mechanism of sorts some change to the process that is taking place in another location. So now we're talking, in the simplest case, just two processes that need to communicate some change. So the process in another location has to first complete whatever it's doing and then communicate some results back to the first process. So they're kind of cross-talking. And this latency, this gap in time, occurs precisely at the I/O border. So if we imagine start on the left, hitting the I/O border as the time progresses from left to right, then it takes a while to reach its end. Then this gap is called latency, this kind of a two-sided arrow from start to end. It takes some time. It's not instantaneous. When the latency occurs, such as described previously, the process on the other side of the border, in another location, is waiting on the process on this side of the border to complete. So they're kind of in a holding pattern. And this waiting is part and parcel of the continuity that is implied by the imperative programming model, which we described earlier, where waiting is kind of akin to pressing the pause button. So I'm like, okay, you wait here, don't do anything until I tell you that everything's okay, you can proceed. The imperative programming model. So one thing to notice is that this process on the other side of the I/O border is fully occupied doing nothing while it awaits for the other process to complete. And in other words, that process that we push the imaginary pause button on is idling. And the bottom line is it's wasting CPU cycles. It's not doing anything useful. In technical terms, such situation can be described with the term blocking. The idling process is actually blocking. And with that situation, when that occurs, we can expect delays. In situations where we have issues with scalability and response time, which is for most of the current apps, it's very important to be responsive and reply to the user request in a very swift manner, but also at the same time, while doing that, be able to handle many incoming simultaneous requests. So that's scalability. It needs to scale as well as be very responsive. And when that occurs, this blocking is very bad, because blocking implies latency, which means users are waiting, there's nothing happening. Also, blocking means that no other calls can come through. And it's a double whammy. It's really a very bad situation that can cost business a lot of money in terms of both a lot of damage in financial and reputation. This blocking consumes computing resources and becomes a performance bottleneck. So it's costly. It's any way you look at it, doesn't seem good from the business perspective. So now we have a problem, and how do we solve this bottleneck? That is the question, and a lot of the work that's going on right now is actually addressing this bottleneck. And on many projects that you may join, you will see people are focusing their efforts on identifying the bottleneck, removing it, or minimizing it. So the only way to actually do it is to give up on discontinuous or sequential execution, because as soon as we are doing this sequential execution step by step while everything else waits, we are blocking. There's no other way to deal with it. And we need to switch over to adopting discontinuous or parallel execution. So now we need to re-engage the computing resources and not let so many resources just idle and being fully occupied doing nothing. So when a process or a thread reaches the I/O boundary, and naturally at that point, if we are following the imperative programming model, it goes into a blocking mode. That's like the knee-jerk behavior. We need to design it in such a way that it relinquishes control. It does not hold and block. It gives up, free up the resources. That is very important. So, for example, if we have such a silly illustration where we want to free up system resources, user resources, etc., we, at that point, in our design, in our implementation code, we want to make the blocking process or thread take a break, take it easy, maybe step back and let others take over. So that is another way of saying we need to switch to asynchronous programming, which is not synchronized and is happening independently. And that is the mantra async that we are now talking about, which basically brings us to the end of the part 2. We need to think about these things before we are ready for the part 3, because once we digest this information, we need to look more closely into the issues surrounding asynchronous programming. So not everything is rosy. There are, not to be naive, but as many problems as asynchronous programming removes, it introduces some other concerns that we need to address. So join me next time for the part 3, in which we will look more closely into the issues, and we need to understand them really thoroughly, not just jump head first into the asynchronous programming. And in the meantime, maybe go back and review the notes, and at the end of this presentation we will publish the email address where you can send your questions. And I hope you'll be having fun with this, and we will talk soon. Bye.